Chapter 7, we want to look at the biochemistry of carbohydrates and then take that a little bit further and try to get a little understanding of why glycobiology is so important. So let's start with a look at what is a carbohydrate. In order to be classified as a carbohydrate, the molecule must have this structure shown here. Carbohydrates themselves have many functions within the body. A lot of time in this course will be spent looking at carbohydrates as an energy source as well as an energy storage. As we get into biochemistry 2, we'll look at how we make carbohydrates, how we break them down to produce energy, as well as using those breakdown products to produce other molecules within the body. We'll do a little bit of work with how carbohydrates can serve as a structural component. I have on this slide as cell walls, but carbohydrates as well as some conjugates are very important in the extracellular matrix around the cell, so we'll look at that some. And then very briefly, we'll get an idea of how carbohydrates can help us with cell-to-cell signaling. It's a really, really interesting subject matter. We'll just try to get into that a little bit. A little bit of terminology with carbohydrates. We have single monomers, and we call those monosaccharides. As we combine two monosaccharides together, we form a disaccharide. And then typically anything 20 plus monosaccharides would be considered a polysaccharide. We can take any of these polysaccharides or the monosaccharides and we can link those to proteins, forming both glycoproteins and proteoglycans. So as we finish up this lecture, you should be able to tell the difference between those two, but just in general, a glycoprotein is going to have a major component that is a protein. So it's mainly going to be protein with some sort of carbohydrate stuck to the protein. With the proteoglycan, in this instance, the major component is going to be sugar, more specifically common disaccharides that we're going to look at, and then we're going to add a few amino sugars to the polysaccharides, and we're going to see how this works towards the end of the lecture. So let's look at our basic biochemistry of carbohydrates. Hopefully this is a review for at least the next few slides, and then we can get into some things a little bit more in depth. So when we're looking at our monosaccharides, our most simple form of carbohydrates, they can come in one of two forms. We can have an aldose or a ketose. This is the most simplistic aldose that we have with the 3 carbons. This is glyceraldehyde. You can see this is the aldehyde function on the end at the number 1 carbon. The most simplistic of our ketoses is shown here. This is dihydroxyacetone. You can see this at number 2 carbon here in the center. This is your ketone group. When we think of our carbohydrates, a lot of the carbohydrates can exist as enantiomers. In fact, the only carbohydrate that does not exist as an enantiomer is dihydroxyacetone phosphate. To be considered an enantiomer, it has to be able to form 2 stereoisomers that are not superimposable mirror images. So the way you figure this, if you go back to your chemistry background, you're going to have this central carbon has 4 different groups attached. That allows this to be a chiral center, so you can have 2 enantiomers. With these sugars that we're looking at, we have that form enantiomers. You can have the D or the L enantiomer. So most of the hexoses that we're going to deal with in humans will be in the D form. So all the images we're going to see from this point out, unless specified otherwise, is going to be the D enantiomer because that's the most common. Now, with these chiral compounds, we can draw them a couple different ways. Typically, we're going to see the sugars drawn in these Fisher projection forms here. So anything horizontal is going to be coming out of the screen towards you, and anything that is vertical is going to be more pointing away from you. So we don't draw the little triangles and the little dashed lines. We just understand that if it's horizontal, it's coming out of the screen. If it's vertical, it's going more into the screen. And so when you're here on the carbon that you're, and I'm going to show you this in a little bit more detail, but when you're looking at your carbon that is going to determine whether you're D or L, when it's on the right like this, you're going to call that D, and when it's on the left, you'll call that L. So let's get to something a little bit larger than the 3 carbon, and I can show you how we name these monosaccharides a little bit better. So looking at these 2 images here, the first thing you need to think about is how you can number your carbons. So you're going to number your carbons. Number 1 will be the carbon that is really nearest or closest to the end of the chain where you have your ketone or your aldehyde. So in this one example, we have fructose. This is a ketone, right? And so the ketone is closest to this end here where you see the cursor. So this would be carbon 1, 2, 3, 4, 5, 6. Okay? So that's how we name our carbons. The way we determine whether we're looking at the D or the L is we're going to use the carbon that is most distant from the carbonyl carbon. So that's how we're going to designate as D or L. So in this example, here's your carbon, the chiral carbon that is most distant from the number 1 carbon. And see, we have the hydroxyl group here on the right. So that's going to be the D form of fructose. Opposite here, L for left. That's how I could always remember that. And so you think, well, why are we looking at this number 5 carbon and not number 6 carbon? 6 is most distal from the ketone. Well, actually, the 6 carbon is not a chiral center because 2 of its groups are hydrogen. It has 2 of the same groups extending. So it's really important to go through a few examples of these to make sure you understand how we name the sugars so that you can go even further, okay? So now remember, as I said, from here on out, pretty much all of what we're going to see is going to be in the D form. And so the D form tells us that looking at this carbon, we're in right-handed hydroxyl group. So when we get to something a little bit larger than our 3 carbon sugars, we may have more than just an enantiomer to consider because we have more than 1 chiral carbon. So we can have more stereoisomers. So if we have a stereoisomer that is not a mirror image, so it's not an enantiomer, we call that a diastereomer. So if we come down and we look now at our 4 carbon sugars, and these are our aldoses, we have aldehydes on the end. We have a erythrose and a threose. These are not enantiomers. So there is an enantiomer of erythrose. We would have L-erythrose. We would have L-threose. Erythrose and threose, though, are both compounds that exist in they're shown here in the D format, but they're different from each other just at one of these carbons. So you see how one hydroxyl group is switched around? So these are going to be diastereomers of each other. When you get even more carbons involved, you can have a special type of diastereomer called an epimer. An epimer is going to be 2 sugars that differ only in the configuration around 1 carbon atom. So if we consider glucose to mannose or glucose to galactose, they are going to be considered epimers. So specifically at carbon 2, mannose is the epimer of glucose. And then similar at carbon 4, galactose is the epimer of glucose. Now all of those slides are just to make sure you're familiar with terminology. So when you hear diastereomer or epimer or enantiomer, you have an understanding of what's going on there. We're simply looking at directionality of which direction the hydroxyl groups are facing when we're looking at these particular types of molecules. All right, so question of the day, which of these sugars am I responsible for drawing? Because you guys all know that I really enjoy forcing you to draw things to make sure you understand. I took these figures straight from your textbook. You are responsible for the ones that are in boxes, okay? So as we start with our aldoses, we've got 3 carbon aldose is glyceraldehyde. 4 carbon aldoses, we have erythrose and threose, stereoisomers that are not enantiomers. These are diastereomers. Moving to 5 carbon, we have ribose, arabinose, xylose, and lysose. Obviously, can't pronounce it correctly, not a real common sugar. Okay. Moving to 6 carbon, we get even more stereoisomers. The most important of these for you to be familiar with would be glucose, mannose, and galactose. So those are all of the aldoses. Now looking at your ketoses. So here's the simplest ketose, dihydroxyacetone, only one that can't be an enantiomer. We have, so you notice there's no D or L listed. 4 carbons, 5 carbons, 6 carbons. So just make sure you're familiar with those structures. So let's take a look at the some common chemical reactions that we can observe when we are looking at these monosaccharides. So if we have an aldehyde or a ketone, those carbons are going to be electrophilic. So they can readily react with anything that is nucleophilic. So when you have the alcohol approach, the oxygen of the alcohol is a nucleophilic molecule. So we can get a nucleophilic attack from the oxygen in the alcohol group. So starting with the aldehyde here, you can have a reaction where you form a hemiacetal. This is what we're going to see when we cyclize these structures to form our cyclic monosaccharides. All right, and we can actually even take this hemiacetal because it still has a hydrogen that we can react with here, right? And we can go even further and form an acetal group. Similar with our ketone, it can react with the alcohol, forming a hemiketal. And again, we can go a step further, forming a ketal. So step 1, forming these hemi groups, that is to produce your cyclic structures. Forming the acetal and ketal, we're going to see that when we form glycosidic bonds as we keep going. So this slide really just wants to make sure that you understand the chemistry involved. So let's take a look at how we actually cyclize these reactions. Okay, so if we take glucose, we can have carbon, the alcohol located on carbon number 5, can react with our aldehyde group. So we get the nucleophilic attack from the alcohol onto the electrophilic carbon, and we form a hemiacetal. When we form the hemiacetal, we end up with what we call our anomeric carbon, and with the anomeric carbon, we can get 2 different versions. In the alpha, we're going to see in the alpha we've got trans format where the hydroxyl group is pointing down. So pointing down means in trans compared to our number 6 carbon here. So that's alpha. If we have the hydroxyl group pointing up, that's beta. That's going to be in the cis conformation on the same side of the ring as our number 6 carbon here. So you need to be familiar with what that alpha and beta means, and we're going to do some drawing and practicing with that. So once we get our rings formed, if you have an aldehyde, you're going to form a 6-membered ring called a pyranose. If you have a ketone, you're going to form a 5-membered ring called a furanose. We typically draw our pyranose and furanose rings with our anomeric carbon on the right side. So remember what that anomeric carbon is. The anomeric carbon is the carbon where we had the attack. So right here, the nucleophilic attack happened on your carbon. That becomes your anomeric carbon. Okay. All right, so how can we compare our 2 structures? If you learn your Fisher projections, you don't have to memorize again to learn your Haworth projections. They're the same thing, okay? So if we take a look at this, we take our carbons, and we start with number 1 because that's our anomeric carbon over here, and it could be number 2 if you've got a ketone you're going from. But so we start with the lowest numbered carbon here, and then we're going to take them clockwise. Okay. Then we're going to look at our hydroxyl groups. If it's to the right in the Fisher projection, it's going to point down. If it's to the left in a Fisher projection, like this one here, it's going to point up. Okay. Glucose, and I'll be honest, the way I kind of always learn these is I would say, so I would do down, up, down. Galactose is down, up, up. So you just kind of have to learn your own way of memorizing them. If you're memorizing the Fisher projections, you do right, left, right. Where I did down, up, down. Same thing. Okay? Once you get familiar with your cyclic structures, then you need to take it a little further and start learning some of these hexose derivatives that are going to be important. And we're going to look at these a little bit more when we get to our glycosaminoglycans that we're going to look at in a minute. But just to point out a few of these that are incredibly important, when you hear glucosamine, you should immediately recognize I've got a glucose molecule and then I've got an amine attached to that. Acetylglucosamine, acetyl group attached to an amine. Okay. So just really kind of become familiar with some of these structures. No, you don't have to draw every single one of them, but you need to be familiar with them. So if we're going to take our monosaccharides and go any larger with these, forming a disaccharide and ultimately a polysaccharide, we need to understand the glycosidic bond. To make a glycosidic bond, we have a hemiacetal group, or a hemiketal, where we've already taken the linear structure and formed a cyclic structure. And then we can have another nucleophilic attack from a hydroxyl group, shown here. And when they interact with each other, we end up with an acetal. So water's removed again. So at the beginning, we had alpha glucose, and over here we have beta D-glucose. So this is my number 1 carbon. Okay. So when we form our glycosidic bond down here at the bottom, we have a 1 to 4 bond, and it's going to be an alpha 1 to 4 because the hydroxyl group, or the oxygen group we now have, is pointing down from the anomeric carbon. So alpha glucose 1 to 4 glucose. Still have an anomeric carbon that's a hemiacetal, so we could add another monosaccharide to this. So here's another example. We want to name this. Okay, so first I'd have to look at my structure here and figure out what's going on. What have I got? Okay, and so I say, okay, here is my number 1 carbon. So it's in the alpha position, correct? So alpha, and I look at my hydroxyl groups, down, up, down. So this is a glucose. So this is alpha glucose 1 to 2. I recognize with my alternating hydroxyl groups that this is a fructose, and this fructose is in the beta position because we have it up. So this is 1, 2, so I have it up here. And so this would be alpha glucose 1, 2, beta fructose. Now, I'm saying it very different than what's written here, right? This is the more complex version. There's nothing wrong with naming it this way. There are a few disaccharides that you really need to know just by the name of them. Maltose would be one. Maltose is going to be your 2 glucose stuck together, a 1 to 4 linkage. Lactose is going to be beta galactose, 1,4 glucose. Then sucrose is going to be beta fructose, then 1 to 2 alpha glucose. So you just need to kind of learn those 3 really important disaccharides. So continuing, let's look at some polysaccharides. Polysaccharides are pretty important to us biochemically. Polysaccharides can exist as homo or heteropolysaccharides. So you may have a polysaccharide that's formed of all glucose molecules, or you may have one that's formed of glucose, galactose, glucose, galactose. They can be just linear, or you can have branch points. Okay? So since you can have a lot of differences here, you don't get that specific defined molecular weight that we see with our proteins. So there's a couple polysaccharides that we're going to look at that I think are important for you to know. And the first one is glycogen. Glycogen is a homopolysaccharide. It's only composed of glucose. To produce a glycogen molecule, you're going to need amylose. So this is amylose, the linear chain of alpha 1,4 linked glucose molecules. To make this glycogen, then about every 8 to 12 residues, you're going to attach in an alpha 1 to 6 linkage another amylose group. So this is going to be the important storage polysaccharide in animals. So this is one you need to know the structure of. Comparing glycogen to our storage polysaccharide in plants, we have starch. Starch is a mixture of two different homopolysaccharides. It's still just glucose, but instead of having just chains of amylose connected by that beta 1,4 linkage, starch is amylose and amylopectin. So it's just a little bit different. We use glycogen and starch as our storage polymers because it has many non-reducing ends. So it's very easy for us to add a glucose or take a glucose off whenever we need it. So as humans, we have enzymes that can break down those alpha linkages. When we compare that to cellulose, cellulose is a glucose monomers connected by beta 1,4 linkages. So as humans, we don't have an enzyme to break down those beta linkages. And that's just what this slide says here. So let's take a look at some of these more complex carbohydrates and glucoconjugates and things that you may not be quite as familiar with. We take these more simple monosaccharides and disaccharides and we attach those to other molecules to give us some really specialized functions. Okay? And this is where we can get a lot of cell-to-cell communication, protein labeling. Some of them are structural. So a lot of interesting things going on. So I want to take a look at some of these with you. First, let's talk about the glycosaminoglycans. Glycosaminoglycans are repeating disaccharide units where one of your monomers is always going to be N-acetylglucosamine or N-acetylgalactosamine. The other monomer is always going to be modified in some way to be extremely negatively charged. Those high volume of negative charges allow a lot of water interaction to help minimize the charge repulsion from all those little negative charges. So glycosaminoglycans are heavily hydrated and they can hold a lot of liquid for us. We find a lot of these glycosaminoglycans in the extracellular matrix of our connective tissue and within our joints. And so we're going to look at that in a little bit more detail here. Here's some of our common GAGs, our glycosaminoglycans: hyaluronate, chondroitin sulfate. You need to pay attention to the structures. Notice lots of negative charges. Keratin sulfate and heparin. Okay? Again, lots of negative charges floating around. So these glycosaminoglycans are the main structural component of proteoglycans. Proteoglycans are going to be your GAGs all stuck on a core protein. And so I want to show you what this looks like. So this is just another slide showing you the GAGs. So with these proteoglycans, we form what we call this bottle brush structure. So we'll have a core protein, and then we'll take these GAGs and connect through this very common linkage. So we always have a serine residue found in the core protein connected through a trisaccharide of xylose and 2 galactose molecules, and then we start adding those repeating disaccharide GAGs. So we end up with this central core protein and all of these negatively charged gags attached. So the negative charges repel each other, and you end up with what looks like a bottle brush. And so here's another image to kind of show you what that looks like. So we have this, in this structure with the proteoglycan, we have hyaluronin in the center, and then each one of these little feather-looking things sticking out is your core protein, and each core protein has a bunch of gags stuck on there. So in the body, you have water stuck in between all of these negative charges, keeping them away from each other. And those negatively charged molecules holding the water allow the proteoglycans to give us their important function. And so if you consider the proteoglycans, for example, in the synovial fluid of joints, then you'll have all of this water stuck in this synovial fluid. And when you have compressive force, it's going to press down and push all the water out. And then when the force goes away, the water can go back in. So it acts like a shock absorber for us in our joints. All right, so those were the proteoglycans. So what's a glycoprotein? A glycoprotein is going to be mainly a protein structure with a oligosaccharides attached. So you can have O-linked sugars or N-linked sugars. With an O-linked sugar, they're always going to be attached by its anomeric carbon through a serine or a threonine residue. So you have an oxygen. If you've got an N-linked oligosaccharide, it's always going to be attached through the nitrogen of an asparagine residue. These carbohydrates are going to help us with a lot of protein recognition, and you'll talk about these when you're in your microbiology class and looking at how viral proteins are glycosylated. That helps them evade our immune system. They kind of mimic us. So lots of importance for this, but for my purposes, I need you to structurally recognize what's going on with the glycoprotein and the proteoglycans. I highly recommend to you that you spend time learning the biochemistry of your monosaccharides, understand those chemical reactions forming the hemiacetal and the hemiketal. How can we form a glycosidic bond? Know your basic structure of your polysaccharides that we discussed, and then be able to structurally and functionally compare your proteoglycans to your glycoprotein.